Hello everyone, I'm recording this lecture to cover topics which we had in class, going through a couple of examples and explain how sequential circuits are designed. Okay, a very fast review on what we did in class. We're trying to design a circuit which looks for prime numbers, 4-digit prime numbers, within an input stream of digits. For instance, if I have um, number as 0101, since it's 5 and 5 is a prime number, my output will be 1. If it finds a prime number, output will stay 1 for 1 clock cycle till next prime number is found. Here in this example, we are looking into overlapping digits, means first 4 digit, then the next one will be shifted to the left, and then another one, and then another one after each other. Numbers in binary, 4-digit prime numbers can be 2, 3, 5, 7, 11, 13, as these patterns here, binary numbers. As we did in class, here is the state diagram of the circuit. Well, I have to mention that between what I have here and what we did in class, there is a small difference. In class, we implemented the circuit with 8 states. Here, I eliminated that extra state that we had. Well, that state is gone. Now I have lower number of states, 7 states from S0 to S7. Please double check that and make sure that you can do that yourself, similar to what we did in class. For example, just to go through one example, when our circuit starts at startup, will be at state 0, assuming that we have receiving all zeros before. So if you receive another 0, you stay in the same state and your output will be 0. If you receive a 1, state will be different. You are moving to state number 1, but your output is still 0, because what you have had is, well, a string of zeros and just one as input. So your 4-digit number will be 0001, which is not a prime number. At state 1, if you receive 0, you go to a state 2. If you receive 1, you go to state 3. So at state 2, for instance, what we have had is we had probably a number of zeros before. We don't know how many. We don't care how many. We have had 1, then 0. Now look at this pattern. You have 0010, which is number 2, which is a prime number. That's why my output is 1, right? And we are in state 2. Similar for state 3. If you receive 1 and then another 1, it means that after a long string of zeros, we don't know how many, you have received 1 and you have received another 1. So your string will be 001, which is number 3, which is a prime number again. So that's why your output will become 1 and your state will be S3. All right, so let's say at S3 we receive another 1. We go to state 5, and what we have will be 0111, which is number 7 and prime again. That's what I have 1 as output, and my state will be different. But after that 1, since you had 1, another 1, another 1, now if you get another 1, an extra 1, like this, so your number will be this. okay, which is number 15 and is not prime, right? So your output will be 0, therefore. And you will stay at state 5 because the 3 recent inputs are 1. You're in the same situation as you were before. You're expecting to get either 1, 0 or another 1. If you get another 1, you stay at state 5 again. If you get 0, you move to state 6, which gives you this input, right? And this will be the new number, which is 14 and is not prime again. Your output will be 0 and your state will change, and so on, so forth. As we discussed in class, as you have seen in other examples, this is the state diagram of the circuit. The next step was, or is now in this presentation, to convert this state diagram to a table. Basically, what we see in the table is the same as you have in the state diagram. It tells the same thing. If you are at state 0, S0, and your input is 0, next state will be S0, as we have it here. You see this arrow points to S0 if you receive another 0, and your output will be 0, which is this 0 here. You see this 0? That's the output you have here, this one. And if you receive 1, you go to S1 here, and your output will be 0 again. So this is the other 0. And 1 after another 1, and any other state. So for instance, let's have a look at what we did for state 4. When we are at state 4, if we receive a 0, we go to state 2 here, and output will be 0, which is that 0. And if we receive 1, we go to state 1, and output will be 1 here, as you can see. Okay, so now the design, the description we had, we get the state diagram, we have the table for states. Next step is assigning codes to states. Assigning code to states. The first question is, why should I assign code to states? The answer is, since you are implementing the circuit in digital, you need to represent everything in digital. If you want to save your state somewhere, which I'm assuming in flip-flops, you need to code them in binary, then save that binary code in flip-flops. How we code assignments, how we assign a pattern of zeros and one to state depends on many different things, different costs and benefits in your design. The most basic, straightforward number assignment is, if I just have state 0, I assign number 0 to that state, like this. If I have if I have S1, I can assign number 1 to it, and so on, so forth. In this example, I have S0 to S6, 7 states. So I can assign number 0 to number 7 to these states. To save these numbers, I need 3 digits and therefore 3 flip-flops. Question is this the only way you can assign codes to states? Answer is no. You can do as you wish. You can do it with 4 bits if you like. You can do it with 5 bits. You can do it with much longer if you wish. But remember, whatever you choose, you have to pay for it as well. If instead of 3 bits, I use 4 bits, I will need 4 flip-flops to save those numbers for my state. Well, if I have them in this order, my design might be different if I use another order of numbers. So, for example, I could do S0 coded as 000, S1 coded as 001, S2 coded as 011, S3 coded as 010, which is similar to gray code. Every neighboring state has only one bit different from another, or many other different ways. I can also look into a state diagram. If there is a transition between two states, I make their code similar and different only in one bit. Well, this is more advanced discussion. This is something that you might want to consider in future in your real design. But remember, in my class, what we do is just numbering like here. Which I admit that this is not the best way. I admit that this is might even end up sometimes to slightly more complex logic. But this is very straightforward. Use that. If you can come up with something better, that also will be acceptable and will be even, I appreciate it if you can find something, a rule, and explain that. I can do it in a better way. So, using these codes, my previous table will be converted to this new table. Well, basically same thing, but instead of writing symbolic S0, I write the number for S0. Instead of writing S1, I write the code for S1. And also for next state as well. If S0 goes to S0, I have the same code here. If it goes to S1, I have code for S1 in place. And so on. For all the states, the same table will be rewritten, but instead of state, codes, symbols, I have these numbers. Next step will be picking flip-flops, designing a circuit to save these values of states. If you are at state S000, let's say I have 3 flip-flops. Flip-flop number 1, flip-flop number 2, flip-flop number 3. This value will be saved in these 3 flip-flops. Other values as well. So these 3 flip-flops are capable of saving every state of my circuit. The main question is how this state will be transformed to this or this state in my flip-flop. Or if I'm at this state, how it can be changed to this and this for different inputs. That's where logic design comes in. That's where we design a circuit to make these changes to the values saved in flip-flops if you get different inputs. Okay, now to implement our sequential circuit using flip-flops, I need to go back, have a look at my flip-flops, and understand how state of an individual flip-flop changes from 0 to 1, or 1 to 0, or even 0 to 0, or 1 to 1. Okay? We have 3 choices in terms of flip-flops: D flip-flop, T flip-flop, and JK flip-flop. Based on what we had before, we've seen that in previous lectures. In D flip-flop, whatever you apply to the input will be saved in your output. Or next state of the flip-flop will be decided directly by input. If you apply 0, state will be 0. If you apply 1, your state becomes 1. So this is very basic. We've seen that. and I'm going to use that, right? For T flip-flop, which is also single input flip-flop, state of the flip-flop change from 0 to 1 or 1 to 0 if you have 1 at input. So if you apply 1 to the input, state of the flip-flop, whatever it is, will be flipped, will be toggled. If you apply 0, however, state won't change. So next state will be the same as current state. For JK flip-flop, situation is slightly different because you have two inputs and state of the flip-flop, next state of the flip-flop will be decided based on what you have as state right now and what you apply to inputs J and K. If you apply 0, 0, state won't change. If you apply 0, 1, state will be 0. If you apply 1, 0, your state will become 1. And if you apply 1, 1, your state will be toggled, will be complemented, will be negated. Whatever you have will be flipped to the other one, 0 to 1, 1 to 0. These characteristics will be used when we want to use these type of flip-flops in larger sequential circuits. But I have to translate that to state transition. It means I need to look into how states will change, under what condition my current state will change to another. Now, I want to have a look at this flip-flop state changes from another point of view. Let's say I have a D flip-flop, input, output, and I know what is the current state. Let's say my current state is 0. The question which I need to answer, since I want to use this D flip-flop in sequential circuit design, if my current state is 0, under what condition, under what kind of input, with what input, this 0 will stay 0 with no changes. Obviously, if you have 0 and you want to keep it as 0, you have to apply input 0. So D must be equal 0. And if you have 0 and you want to change it to 1, you have to change D. D equal to 1. Or if you have 1, you want to change it to 0, you have to give 0 to D. And if you have 1, you want to change it, or sorry, you don't want to change it, and you want to keep it as 1, the only thing you need to do is you must make sure that your input D will be 1 on next input clock. Okay, so for D flip-flop, it's a kind of obvious because D flip-flop is transparent. Whatever you say will be the state. Whatever you apply to the input will be exactly next state of your flip-flop. And it's kind of very basic question if I ask you this. For T flip-flop might be slightly different. For T flip-flop, if I have a T flip-flop and same question. Let's say my current state, my current value saved on the T flip-flop is 0, and I want it to stay 0, no change in the value. So what input I have to apply? Exactly T equal to 0. But if you have 0 as your current value saved in the T flip-flop and you want to change it to 1, you have to apply T equal to 1. If you have 1 right now and you want it unchanged to stay 1, you have to apply T equal to 0. So you have to apply 0 to the input at next clock. And if you have 1 as your current value and you are going to change it to 0, you have to apply t equals 1 at next clock. Okay? Situation for JK flip-flop will be different. Look at JK flip-flop. JK flip-flop. This is output Q and clock. To remind myself what I had on JK flip-flop again, I just do the table again. So Q n plus 1 means next state, and current state Q JK 0 0 0 1 1 0 1 1. My next state will be the same as previous state if I have 0 0. My next state will be 0 if I have 0 1, and 1 0 will give me 1 at next state, and 1 1 toggles my current state. Now, I'm going to ask same question as I did for D flip-flop and JK flip-flop and T flip-flop, for JK flip-flop. Think about this. If I tell you that my JK flip-flop right now has values saved, value 0 saved, what combination of input, J and K, will keep your value, saved value, as 0? What combination of inputs of J and K doesn't change your value? So if you have 0, you want to keep 0, right? One basic answer, obviously, is this. I'm sorry, I apologize. Is this. So if you have J equals 0 and K equals 0, your 0 will stay the same, won't change. Well, having said that, there is another combination of input which do the same for you. Look at table. You want to have 0 after all. One way is, since your current state is 0, to apply 0 0, won't change the state, you'll get 0. The other choice, however, is this one. So if you apply 0 1, your next state will be 0. So that one is also an answer. If your J is equal 0 and your K is equal 1. Two different combinations will give you the answer. Okay, now I can make this even better. If your current state is 0 and you want to stay the same, you don't want that state to change, transition from 0 to 0. The only thing you need to do is K doesn't matter whether it's 0 or 1, right? But J must be equal 0. So your answer will be J equals 0, K is don't care. Or, well, D, or don't care. Just do this. I say that again. I have a JK flip-flop. I know for sure that currently a 0 is saved on my JK flip-flop. The question is, what should I apply to the inputs to keep that 0, not to change that 0? Why I'm doing this? Because in sequential circuit design, I have to think how to change states. Let's say in my example, I'm in state 0, S0. I want to stay at state S0 if input is 0. You remember that in the table? Now, to answer that, I have to think what keeps value 0 of my JK flip-flop as 0. Doesn't change that to anything else. Same story or similar story for other inputs. Now, if you have 0 at your current state and you want to change it to 1, what combination of inputs will do that for you? Your current state of JK flip-flop is 0. You want to change it to 1. Well, again, one obvious solution is this. You want to change your state to 1. Another solution, however, will be this. Toggling the current state. So either you can say, regardless to current state, just make my output 1, or just complement the current state, because I know the current state is 0 and complement will be 1. So there are two combinations of J and K which can give me the same answer. Between these two combinations, K can be either 0 or 1, which means don't care. So the only thing I need to do is J equal to 1, K equal to don't care. So J 1, K don't care will give me that change. All right. Same thing can be done for other transitions. If you have 1 and you want to stay at 1, you want your input, your state to stay 1, one solution will be this. And one is you don't want to change the first one. These two combination of inputs will do this transition for you. Transition from 1 to 1. So can be either 0, 0 or 1, 0. By looking at this, you see that J can be either 0 or 1, but K must be 0. So the transition will happen if, well, J is don't care. It doesn't matter if it's 0 or 1, but if you make sure that K is equal to 0. And last one, I write it here. If current value saved on your JK flip-flop is 1 and you want to change it to 0, what combination of inputs will give you that? Look at our table. What you see, to get 0 at output, one obvious solution is this. Just give me 0 at output. Also, since I know that my current state is 0, the other choice is complement of the current state, which becomes this one. So looking at this, I can see, well, J can be either 0 or 1, but if I apply 1 to my K, this transition will happen. So it would be J don't care and K equal 1. So this explanation gives me the answer to this question. If I have a flip-flop, can be D, T, or JK, and I know what is the current state, what input I have to apply to the flip-flop to make output whatever I want. If you have, let's say, T flip-flop, you know the current state is 1, what input you need to change it to 0 or keep it at 1. Or if your flip-flop is D and your current state saved in the D flip-flop is 1, what can make it 0 or what can keep it as 1? And so, same thing for JK flip-flop as well. Now I have to look at this and apply this knowledge into sequential circuit design. Well, this discussion is briefly outlined in this table. You see that, well, if you want to make a transition from 0 to 0, and if you have D flip-flop, it means that input of your D flip-flop must become 0. If you have T flip-flop, input of T flip-flop must be 0. Or if you have JK flip-flop in your design, you have to apply 0 to J, and K can be a don't care. Same for other transitions. Here we are talking about one single D flip-flop or T flip-flop or JK flip-flop. In a circuit like our example, how many flip-flops I need? 3 flip-flops, because my states were 3 binary digit states: S0, S1, S2, and so on, so to S6 or S7 or whatever number of states you have. Now, I want to do the same thing, following the same strategy. If I have been in S0 and this S0 is making a transition based on input 0 and wants to stay at state 0, and I'm using, let's say, D flip-flops, what I should apply to the input of the D flip-flops to stay at S0? Or what should I apply to the D flip-flop to make a transition to state S1? See, here I have 0, 0, 0, here I have 0, 0, 1. Means if, well, again, I'm talking about D flip-flops for now. This is digit, let's say I call it, well, A, this one B, this one C. So I call this one A, B, and C. These 3 flip-flops keeping 3 digits corresponding to my different states. Now my problem is if A is equal to 0, B is equal to 0, C is equal to 0. 3 flip-flops are keeping value 0, 0, 0. Means I'm at state 0. One input of x equals 0 is coming in. I want D flip-flop A, D flip-flop B, D flip-flop C, all make a transition from 0 to 0. Because I'm not changing my state. My state will be the same. Look at this top transition top here. You see? Since I'm not making any transition from S0 to anywhere else when I have x equals 0, so D3 should stay the same. And when my input is 1, you remember this in the C diagram? When I have input 1, a transition will happen from S0 to S1. Means A will stay 0, B will stay 0, but C must make a transition from 0 to 1. So under this condition, this will make a 0 transition to 0, 0 to 0, but this one 0 to 1. Now, when x is equal to 1, I have to apply appropriate inputs to each flip-flop to make this transition for me. And that's how we design our sequential circuit. So we have flip-flops in, we have table which tells us what sort of transition will happen to the value of the flip-flops for different inputs and different current states. So our design will be based on, let me clean up here. Now I want to design a circuit based on A, B, C, and X, find out what would be A next state, B n plus 1, and C n plus 1. If I call this current state, means AN, BN, CN. So there will be a table, right? For example, again, if I have 0, 0, 0, I'm at state S0. My input is 0. My next state will be 0, 0, 0, right? Why? Because in the state diagram, when I'm at state 0, S0, and input is 0, we will stay at S0. And what is my output? Right, Y here as my output. My output also will be 0. If I'm at state 0, 0, 0, and my input is 1, my state will change to 0, 0, 1 because we are going to state S1, which was coded as 0, 0, 1, and output will be 0. If I'm at state 0, 0, 1, means I'm at state S1, and I get a 0, I'll go to another state, which was, I don't know, I don't remember exactly, it was S2 or S3. Based on that will be next state and output. And you continue on this one by one till you have all the combination of current states, input, and output. When I have that, then I need to think how to change value of a flip-flop from 0 to 0 with these inputs, from 0 to 0, from 0 to 0, right? Or in the second line, from 0 to 0, from 0 to 0, and from 0 to 1 for C. That's my next step of design. Okay, let's do it on the table. Let's do it on the table that we developed for our design so far. Well, if you are not sure, if you forgot how our state diagram was, please refer back to the state diagram I had in a couple of slides before this. What we have here is transition between these states. S0 transits to S0 if you have input 0, transits to S1 if you have 1. 1 goes to 2 if you have 0 input, and 3 if you have input equal to 1. Now, I want to design this using, let's say, D flip-flops. Okay, so the goal is 3 D flip-flops, 1 flip-flop for A, 1 flip-flop for B, 1 flip-flop for C, as I mentioned in previous slide. All of them are clocked. These clocks are connected. So system clock. System clock. I have Q for A, I have Q for B, and Q for C. Or just basically A, B, and C. What we want to do is this. If we are at 0, 0, 0, means A is equal to 0, B is equal to 0, C is equal to 0. And your input is here, top X. And your input is 0. You want to flip-flop A, flip-flop B, and flip-flop C stay at 0. Well, here we have D flip-flops. So the answer is so simple. If you want them to stay at 0, just give them 0. Okay, so if you have 0, 0, 0, 0, and your input is also 0, so you have 4 variables coming into your circuit. One variable is this, another variable is this, another variable is this. These 3 feedbacks. Combined with your X, 1, 2, 3, 4 variables, design a circuit which gives you 0 when you have 0, 0, 0, 0. Or give you outputs of 0, 0, 1 and 0 as your output if you have a, b, c equal to 0 but x equal to 1, and so on so forth for rest of the table. For example, in here, just jumping to state this state, right? Let's say a currently is equal to 1, b is equal to 0, c is equal to 0. If x is equal to 0, then you want a, next a means a n plus 1 to become, you see this one here. You want a to become 0. You want b plus 1 to become 1. And you want c, next c, to stay at 0. And at the same time, this one, see, this one means your output. Also output will be 0. For every single input output, look how many inputs, how many outputs we have here. We have 4 inputs, X, A, B, and C. How many outputs I have? 4. A, next A, next B, next C, and output. For every combination of input, and current state values, you have to figure out how to create next state and the output using this table. Okay, that makes it a classic logic design circuit, a very classic, like what we did with different input outputs combinational circuits, the same thing as we did over there. So the problem will be different just in different type of inputs and outputs. So A at next state will be my output. My inputs are A, B, and C at current state and input. See, where did I get that table? You see combinations 0, 0, 0, 0, 0, 0. This 3, A equal to 0. See, A equal to 0, B equal to 0. Look at table. A is equal to 0, B is equal to 0, C is equal to 0. Input equals 0. Here. Now look at the large table here. A is equal to 0, B is equal to 0, C is equal to 0, X is equal to 0. That's my input. What is output? A at next state. You see? That's where I get that. A, B, C equals 0, X equals 1. My next one will be this. 0, 0, 1 means A0, B0, C1, A0, B0, C1, but X equals 0 means this one. So look, this will go here. Oh, my apologies, wrong. This one goes here. And this one goes here. Change the color. Now, this one, look at this, 0, 1, 0, 0, 1, 0, top here. See that? This one goes there. And this one goes here. Zero, one, 0, 1, 0, this one goes here. And this one goes here. You see that? One by one, all the values from table will be transferred to another table, which is a classic K-map, well, same thing as we did before, but here the only difference is we are using previous values of the flip-flops to calculate next value of the flip-flops. Previous value of the flip-flops plus input, which is X here, plus input, which is X here. So inputs of the table are previous values of the flip-flop and input, and output of the K-map is next state value of the flip-flop. Okay, so here this is a K-map, classic K-map, neighborhood implementation. So you can conclude that the next A or A at next state is related to current state and input as this. Look at that again. Look at that again. I'm going back before I did that. Again, look, current state, inputs, value of the output, which is Y. This is Y. We find out what is the value at next state and output value using current value of the flip-flops and input using a K-map as this. We do the same for B and C and Y. Okay, so as you can see, for each one we have a K-map showing us how next clock value of A, next value of B, next clock value of C, and also the actual output of the circuit are calculated based on current state of the flip-flops and the input value. Gives us this basic relationship between inputs and outputs. Well, this needs practice, definitely. You have to go through, you have to do that. You probably need to watch this a couple of times and do it step by step. It's very, very simple. The only difference is you have to figure out that while you're calculating the next state of the flip-flop based on previous state of the flip-flop and input. And that's the whole concept of sequential circuit design. If I work on this, I can design a circuit for a D flip-flop implementation of our circuit. Okay, 3 inputs, 3 current state as inputs, and input signal X then combined together gives me logic design. For instance, if I implement the first one, I'll get this. For the second one, what I have is 3 AND gates. 1, 2, 3 AND gates. 3 input, For first one, I have A prime, which comes from here, B bar, C bar. So I'm not drawing the lines, just telling you that here I have A bar, B bar, this one, and C. For the second one, I have B, C, and X. And for the third one, I have A, B bar, and X bar. They work together and go here. Remember again, all of these are coming from these guys here. A, B, and C. Well, I didn't want to make it to BC, but if you have B connected here, you have same B connected to this, you have B connected to this one, and you have A connected to this. Same thing goes here. A connected to this, B bar connected, C is connected here. B bar also need to be fed back to the circuit, and so on. All right. So same goes with third one, which is again two AND gates, B bar and X, B, C, and X bar, OR together, and output will go here. Again, this B and C are coming from output of our flip-flops. That would be your circuit. And for Y, same thing. You use A, B, and C coming from there, from output, from current state, combined with X as your input to give you a circuit for your output. This is the flip-flop implementation of our prime number finder. Now, let's design the same circuit using T flip-flops. What I need is the same transition table for states to show me how A, B, and C change to next state based on current state and input X, plus a small reminding table showing how value of a T flip-flop will change if you want to transit and to make a transition from 0 to 0, 0 to 1, 1 to 0, or 1, 1, as we did before. I have it as a reminder just to have a look at when we try to design the circuit. So the design will be 3 flip-flops, similar to what we did for D flip-flops. So TA, TB, TC to produce my next state of B, A, B, and C. I'm going to design a combinational circuit with inputs of A, B, and C plus X to figure out what value of T should be produced to make transition from current state to next state for each combination of input and current state values. To do so, I have to have 3 K-maps for TA, TB, and TC, and also another K-map for output, similar to the flip-flop as we had before. Here are my K-maps. Let's do one of them, and then I give you the solutions. Let's say I want to figure out how TA should be calculated. What are my inputs? A, B, C, and X. 0, 1, 1, 1, 1, 0. Now, look into the table. If current state is 0, 0, 0, and your input is also 0, A is 0, B is 0, C is 0, X is 0. A is 0, B is 0, C is 0, X is 0. We are talking about this square. There will be a transition in A from 0 to 0. A transition from 0 to 0. Based on our table, to do so, we have to apply a 0 to t. So ta for this transition must be 0. If your input is 1, we're looking at this a, which is also 0. This square is when a is 0, b is 0, c is 0, but x is 1. This one. Now let's do this one, this row, just for the sake of example. Do this one. At this row, from A0, B1, C0, look, A0, B1, right? A0, B1, C0, these two. So we are talking about these two cells. Transitions for A, I'm talking about A. For A would be from 0 to 0 if x is equal to 0, means this one, sorry, here, 0. And transition from 0 to 1 if x is equal to 1, which will be 1. See, why 1? Because for make a transition from 0 to 1, based on table, you see here, you have to use t equal to 1. Let's do another row. Let's do another row of my table. This one. Let's pick this one. From state 1, 1, 0, clean this, that one as well. So state 1, 1, 0, so 1, 1, again 0, these two. We're making transition to two other states. So we are talking about these two cells for x equal to 0 and x equal to 1. At x equal to 0, what we have is a will be transformed to 0. See, a from 1 becomes 0. So transition from 1 to 0. Transition from 1 to 0 requires t to be equal to 1. So this one will be 1. This is unlike D flip-flop that whatever you see in the next state, you just have it at your input. But here we have to compare current state and next state. Here I'm making a change from 1 to 0, or from 1 to 1. From 1 to 1, this one, you see, your output, your input to the TA must be 0. So this one will be 0. So we have to repeat that for every single transition, for each state in our circuit. So how many I have? For A, I have this, will be transformed to this, and this, for x equal to 0, and x equal to 1. All the rows, these two are don't cares, we don't have that combinations, right? We don't have that combinations. Rest of them, one by one, need to be examined. One by one, you have to check. Transition from 0 to 0, transition from 0 to 0, transition from 0 in the second row, transition from 0 to 0, transition from 0 to 0 again in third row, transition from 0 to 0, transition from 0 to 1, fourth, transition from 0 to 1, transition from 0 to 1, right? And here, transition from, in the other row, transition from 1 to 0 and transition from 1 to 0. You do that one by one to figure out how your table should be filled with zeros and one to create an appropriate logic for your TA to control transition between states for your T flip-flops. Okay, to do that you have to repeat this for B and C as well to get the answer. As we have it here. So I hope I haven't done any mistake. Please double check, make sure everything is correct, right, based on what I have discussed. For example, for B, look, I'm checking myself on one of the cells for B. Let's say this one. I'm double checking myself. In this one, previous state has been 0, A0, B1, C1, X1. So we are talking about 0, 1, 1, 0, 1, 1 here, this row, and X equal to 1, this one, right? We are talking about B, we are finding TB, so transition for B from 1 to 1. Transition from 1 to 1 means no change, means your T, look at this here, at T table, here, T flip-flop table. Transition from 1 to 1, input must be 0, so this is correct. Please do that one by one. Make sure every single cell of these tables are correct, and then as a practice, write down the functions for T inputs of your logic, T inputs of your D flip-flops. When you have all these, then you can design the circuit with 3 T flip-flops, input TA, input TB, input TC, current state A, current state B, current state C. You have also clock for all of them. I'm assuming these are connected, so clock. You find the logic for TA, TB, and TC. Write them here and connect them to your flip-flops. A function of input signal X and feedback signals A, feedback signal B, and feedback signal C to all of these, not just one of them, to all of these, as many as you need. That will make your circuit. That will be your design using T flip-flop. I suggest you to do that and make sure you can do this down to the last step and you can design your sequential circuit using T flip-flops. Now we can do it with other flip-flops as well. For JK flip-flop, we have the same story, means we are using same table for transition between states. Also, I have to keep an eye on JK flip-flop transition table. What selection of J and K makes a transition from 0 to 0, from 0 to 1, from 1 to 0, or 1 to 1, right? We need to keep an eye on that as well. Similar to what we did with D flip-flop and T flip-flop, we have to examine every current state transition to next state and what kind of changes will happen to each bit of my state. A is transition from 0 to 0. A 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 transition from 0 to 1. And write those down into tables as we have here. As we have how many K-maps I need in this case? I need 6 K-maps, 4 flip-flops, and I need 1 K-map for my output. Similar to D and T flip-flop. Output will be similar, but input of the flip-flops will be different here because each JK flip-flop has 2 inputs. So you need to figure out what logic you need to apply to input J of flip-flop A, what logic you have to apply to K input of flip-flop A, and so on. So I have 3 flip-flops, 1 flip-flop for A, 1 flip-flop for B, 1 flip-flop for C. So they give me A, B, and C. For each one, I have 2 inputs, J, K. J, K for B, and J, K for C. So that will be J, A, K, A, J, B, K, B, J, C, K, C. You need to figure out what logic combination of X, A, B, and C you need to make transition between the state as you have in this table for all of them. That's why I need 6 K maps because I have J, I have K for A, JK for B, and JK for C. Let's do one of these tables and I leave the rest of them for you to do it as a practice, just to make sure you know how to do that. I'll go through, let's say, this one, randomly picking JB, JB, or I can do these two together because they come as a couple tables, okay? So, 0, 0, x equal to 0, x equal to 1. So it will be 0, 0, this column, 0, 0. C is also 0, right? I'm looking into these two cells here and here. Look at values. Look at values. For B, right? These are for B. These are for B. So middle value. Look at middle value. This one. And transition to this middle value here and this middle value here. All right. So transition from 0 will be from 0 to 0 to 0. Transition from 0 to 0, look at JK table here, down here, JK table. To make a transition in JK flip-flop from 0 to 0, what do you need is a 0 on J and don't care on K. So K would be don't care, J will be 0, 0. Going to the next row, we are talking about in the next row, let me clear this up to see what we have. The next row here, from 0, 0, 1, 0, 0, 1, we are talking about these two cells in my table, here and here. Okay, so what I have is B makes a transition to 1 and makes a transition to 1 in both cases. So transition from 0 to 1 in the table means this one means you have to give 1 to j, 1, 1, and x to your k. All right, let's do this one. 0, 1, A is 0, B is 1, C 0. 0, 1, 0. This one, this transition. And again, we are looking into B, how B changes. B changed from 1 to 0 and 0 in both inputs. For both inputs, it will be a transition from 1 to 0. Transition from 1 to 0 in the table gives me this. Gives me this. Yeah, this one, which means don't care on J and 1 on K. So don't care, 1, 1. This one will be same column, but next two rows, I have a transition on B from 1 to 0 and to 1. Okay, transition from 1 to 0 and transition from 1 to 1. For transition from 1 to 0, I have to have this, right? 1 to 0 will be don't care, 1, don't care, 1, don't care, 1. And transition from 1 to 1, don't care, 0, don't care, 0. The other row, this one. Well, we are not talking about output. We have done that already. Will be 1, 0. This one, A is 1, B is 1, C 0, 0. X will be 0 and 1. Two cases. X will be 0 and 1. And we are talking about transition on B, right? We have two transitions. If X is equal to 0, we have B transition from 0 to 1. And when X is equal to 1, we have transition from 0 to 0, right? When it's 0, 0 to 1 means it would be this row, right? 0 to 1. 1, don't care. 1, don't care. And when X is equal to 1, it will be 0, 0, so it will be 0, don't care. 0, don't care. And the other row, this one, transition will be, again, we have combination of 1, 0, 1, so we are talking about this and these two rows based on C equal to 1. So transition is from 0 to 1 and 0, 0. From 0 to 1 and 0, 0. Transition. So in this case, if X is equal to 1, I have a transition on B from 0 to 1. And when X is equal to 1, I have a transition from 0 to 0. 0 to 1 will be 1x, 1x, and transition 0 to 0 will be 0x. And the last row of my table, just doing that, and I'm going to stop this, will be here. See, on B, I have when X is equal to 0 here. B makes a transition from 1 to 0. And when X is equal to 1, B makes a transition again from 1 to 0. Both cases, B becomes 0 from 1. All right, 1 to 0 means here, means X 1, Here's x, 1, x, 1. And I don't have these two anyway, which be x, x, don't care. So let me do those with different color just to make sure they're coming from somewhere else, because we don't have that in our transition table. So writing down the functions based on this table would be very easy. Would be very, very easy for you. I'm sure you can do that. So many different ways. These for our neighbors. These for our neighbors as well, right? And these two are neighbors with these two down here. Okay, which gives me a very simple function. And also this one neighbor with this, right? And all these for our neighbor with each other. So KB will be based on what I have, assuming I haven't done any mistake, will be just C bar or B X bar. Yeah. And for this one, JB will be C X bar, or what I have is A bar C, or the other one is A X bar. That would be your J and K for B, just for B. Please do that for A and for C as well. Make sure you know how to do that. Exactly follow the same steps as I did, and hopefully you will be master of this in just some few exercises. Another topic or important characteristics of sequential circuit which we need to look into is the concept of milli and more circuits. Milli and more circuits are both sequential circuits, but the difference is when you are talking about a milli circuit, it means that at each state your output might have either 0 or 1 values. But in the Moore circuit, at each state, your output can be only one of these. You can't have them both. All right, so sounds clear. Let's have a look at this. In my previous example, if I tell you that my circuit right now is in state S0, can you tell me what is your output right away? If you go back and have a look at that state diagram, you see at S0, you're always, if your circuit is at S0, your output will be definitely 0. But this must apply to all states, right? If for all states of a state machine, of a finite state machine, of a state diagram, of a circuit, if you check every single state and see, just knowing which state your machine is in right now is enough to make conclusion that what is the output, that circuit is a Moore circuit. Basically, looking at milli and Moore circuit, you can say if you have a milli circuit, your output is a combination of state values, content of your flip-flops, and combined in a combinational logic with inputs. In Moore circuit, your output is calculated only and only by states. So look at these two circuits. My output, in one of them, output is a function of states, of current states, plus inputs. In the other one, your output is only function of states. Well, be careful, be careful. It doesn't mean that your output doesn't follow input, but they're not connected directly. So input will change the states and state will change the output in Moore machine. In Mealy machine, the inputs will change the state and at the same time they might change the output directly as well. Why this is important? Why we do care even about having a Mealy or Moore machine? The reason goes back to the concept of synchronization again. Look at these two scenarios I have here. Let's say you have a clock, and this clock keeps track of a change of everything in your circuit. You know, disciplines every signal change in your circuit. But you have an input which comes from another source. Someone, you know, pushing a button, turning on and off, doing something coming from another circuit, which is not necessarily synchronized with your circuit. So it might be possible because there is a change in your input unsynchronized with your clock. Output of your circuit will change because this input directly affects the output and states as well, right? But here, if you have same input to a Moore circuit, these changes of input must go through changes of states first, make some changes in the state, and your output always goes from a state which are correctly synchronized with your clock. So your clock is always applied. Doesn't let any out of clock change in your output. But in Mealy machine, it might happen. It might happen, well, not necessarily in every circuit, but based on your logic, based on your circuit, how you used it, it might happen. So it means if you want to decide which one is more preferable, which one is better, so generally Moore machine is better synchronized, more disciplined, your clock has a full control on your output, but in your in Mealy circuit, you not necessarily have full control of that, right? So going back to our design, if you look at your Y output, if your Y output is only and only function of A, B, and C, then your circuit is Moore. It's this one. But if your output is a function of A, B, C, and X, that's a Mealy function. Mealy machine. That's a Mealy machine. Mealy machine are not synchronized. So why we ended up to Mealy machine? Because we did try to minimize our states. Remember, every Mealy machine can be converted to Moore machine and vice versa. And normally, Mealy machine normally have less number of states. Okay, that's why we end up to Mealy machine. Doesn't mean every minimization will make your design a Mealy, but what we can say, two machines with the same behavior, with the same original description. If you implement it in Mealy or Moore, normally Mealy machine is simpler, cheaper, to implement. But it has problem with synchronization because it follows input as well as your current state. For example, have a look at this state diagram here. What do you think? Is it a milli machine or a Moore machine? Check, check. The checking is if you are in a specific any state, just pick any of them. Let's say here, as I said, S0. If you're at S0, can you say definitely what is your outputs? If I'm at S0, I might have come to here through this, which gives me an output of 0, or through this, which is output 0, or through this, which is output 0. So if you tell me my machine is right now at state S0, I can definitely tell you that your output is 0. If you are at S2, however, you can say that it might be 0 when you transfer from S4 to S2, or can be 1 if you are coming from S1. So you see these two are giving you two different values. So this is a milli machine. Another example, another design example. Let's say we want to design a circuit which looks into a sequence of zeros and one and looks for 3 or more ones coming after each other in your sequence. If you have 3 ones, each time it finds 3 ones one after each other, gives you 1 in one clock cycle. And next clock cycle, again, checks the input. If still has 3 input ones, it gives you 1. Otherwise, it gives you 0 as your output. To design the circuit, again, similar to the previous one, we have to have a state diagram. In the state diagram, well, based on operation, based on what you have S0 start up state. Your machine goes to state 0 when it turns on. If you receive 0 after each 0, it will stay at the same state. First one will transfer your state to S1. At S1, if you get another one, you go to S2. But if you get 0, means that the one which you have found is useless and it needs to go back again and start over. When you find second one, if you get a 0, you go back to state 0. If you have 1, this is a typo from book, it should be 1. If you get another one, you go to S3, I'm sorry, you go to S3. At S3, you have found at least 3 ones after each other. One transferred you to S1, another one transferred you to S2, another one transfers you to S3. From now, any extra one you find will give you a longer number of ones one after each other. So new one stays at the state S3, but if you have 0, this is also typo, if you have S0 here, that will transfer you to S0 and start over searching for ones after each other. First of all, question number 1, is this a milli machine or a Moore machine? By looking at states, well, we figure that for each state, if I tell you your machine, this state diagram, is in that state, you can right away say what is the output. If it's at state S0, definitely output will be 0. No chance for any other output. If it's at S1 or S2, also your output will be 0 because it means that you don't have enough ones to give to create one output. But if you're at S3, your output will be definitely 1. So this makes this machine a more machine. To design that, I need a state table. I need to assign code to my state. So I do similar as we did. So state S0 will be coded as 00, state S1 as 01, state S2 as 10, state S3 as 11. How many flip-flops I need? How many flip-flops I need? 2. One to save this, one to save the other one. So table will be combination of current state and input, which gives me next state and output. Similar to what we did, we can use this table to design our circuit using D flip-flop, T flip-flop, or JK flip-flop. Okay, let's have a look at our table. Again, as I said, same strategy. If you want to design, you have to look at A and B and X as your inputs, and your output will be next state for A, next state for B, and Y. If you use D flip-flop or T flip-flop, you need 3 K maps for A, B, and Y, or inputs of your flip-flops for DA, DB, or Y, or for TA, TB, and Y. And if you use JK flip-flop, you have to find JA and KA, also JB and KB inputs of your flip-flop, and again Y. Y would be the same because Y is calculated based on your current state and input anyway. Won't be different between these three, but using different flip-flops means that you have to have different set of K-maps. What is the size of the K-maps? What is the size of the K-map? It depends on number of inputs, right? Number of inputs to the circuit. In this case, I have current A, current B, and X as my input. So I will have 3 variable K-maps. If I use D flip-flop, this would be the solution. For D flip-flop, as we mentioned before, it's transparent. Whatever you want your next state to be, you just have it in the input of your D flip-flop, and that will do the job for you. So for each of these, you'll find the logic. What is the input of the D flip-flop as a combination of input and states for D flip-flop A and B, and also for your output D. After simplification, you find the functions. Implementation will be as you have here, similar to what we did before. Again, feedback from A and B, or A bar and B bar if you need them. Go back to the circuit to apply what you need as input to your D flip-flop to create a change of states. Here, interestingly, you have to look at Y, which is only a function of, as you can see, A and B. This is a Moore machine. So output is calculated only based on states, not input directly. Input change that state. So your output is indirectly affected by input. So input change the state, and states will change your output. If you want to redesign the same circuit using JK flip-flops, as we did before, well, I mentioned that you need J to have JA, KA, JB, KB, and also output using to have JK flip-flop design. Also, I suggest, even in exam or wherever you want to design, have a small transition table of JK flip-flop in front of you to help you to figure out how these changes will happen from 0 to 1, 1 to 0, and what sort of J and K combination you have to apply to your flip-flops to make that transition. From this table, we figure out, for instance, if you have 0, 0 and input is 0, your A will stay at 0, your B will stay at 0. If you have this combination, however, A will be 0 again, but your B will change to 1. All right, so with this, you can make the design. So values are calculated based on that. Please go ahead, make your own calculations. Make sure these results are correct. These results are coming from correct calculation. For example, I can do, let's say, just randomly pick this one to see if you're doing, have done a correct job. So 1, 0, 1, 0. We are talking about A equal to 1, B equal to 0. So it would be this column, right? This column in all the tables. And your input is 1. Your input is 1. So it will be this row. This row. So we are talking about this cell in our designs, right? So A change from 1 to 1. From 1 to 1. You see, change from 1 to 1 means J is don't care and K must be 0. So A is don't care, you see, and K must be 0. B is change from 0 to 1. Change from 0 to 1. Change from 0 to 1. You see? Means this one. Which means J must be 1, K don't care. J must be 1, and this one don't care, which are correct both. Okay? And your output is 0. Your output is 0. Your output is 0 when A is 1, B is 0. See here. And so on, and so on. You can do that for every single cell and see as what I have done here in the slide, the actual slide, not what I'm writing. See, all of these are calculated by just checking what transition happened. That transition will happen based on what combination of J and K in your input, and that fills up your table cell by cell for both J and K of A and J and K of B. When you have all this done, designs for J and K for A and B will be done, and that will give you the circuit to be applied to J and K flip-flop. This is for A, this is for B. And also you can design your Y using a circuit. We can do the same design with T flip-flop as well. The only difference will be you have to follow a different transition table. Transition between different values of T flip-flop based on input, as we did before for JK flip-flop. So again, if I pick one row to test my knowledge on how can I do that, well, A equal to 1, B equal to 0 will be this, right? For your current and next state at x equal to 0. So we are talking about this cell, and this cell, right? So A is flipped. A is flipped from 1 to 0, means you have to have, I'm sorry, here. You have to have 1 here, but no change in B, so B will be 0. And your output also will be 0. In that way, you fill up the table. Every single value in the table will be calculated based on that, and you have a design here. And you can make your circuit implemented based on that, like this. When it's implemented, every cell of your T flip-flop input tables are filled up, and then you can design the circuit using this logic simplification. Another example, very popular example, is counter. When you have a 3-bit counter, for instance, counters are circuit which count numbers, binary numbers. Let's say if I'm talking about a 3-bit counter, it counts from value for each input or each clock cycle. It counts up value 0 to 1. So you have 0, 1, 2, 3, 4, 5, 6, 7, and when it's done, it goes back to value 0. Different type of counters. There are a lot of different combinations. One of the simplest one is like this. It counts one after each other. 0 goes to 1, 2, 3, 4, 5, 6, 7, 6, 7, and 0 again. And it's called an up counter. Means with each input or each clock cycle, it counts up. You can also do down counter. You can design another counter which counts down. It starts from value and goes to the previous value at each clock cycle. Transition table for counter will be something like what we have here. You see transition from 0 to 1, from 1 to 0 as numbers. But in terms of states, you have to check that 0 is transferred to 1, this 0 stays 0, and this 0 stays at 0, right? How many flip-flops I need to implement this? Since I have 3 variables, I need 3 flip-flops. Probably the most popular or the simplest implementation of a counter will be using T flip-flops. Why? Why? Because when you look at the implementation of this, look at this. Each state for A, you see each time it will be toggled. Look at this. Check this. See, every single time A0 will be toggled. So that's why you only need to apply 1 to your A, because every single clock, this bit of the counter will be flipped, will be toggled. So you apply 1 to the T flip-flop input of the first bit, of the LSB bit of your counter. How about A1? Look at A1. Is it the same scenario for A1? Every clock cycle it toggles? No. You see here it doesn't toggle, but here it toggles. Here doesn't toggle. Here toggles. Here no change. Here change. No change. Here change. So every other time it changes. Or it's better to say if A0 is 1, then it changes. You see that? If A0 is 1, it changes. Every time A0 is 1, you see A1 changes. A0 is 1, A1 change. A0 is 1, A1 change. A0 is 1, A1 change. That's why in your design you see it's equal to A0. The input of the T flip-flop for the second bit is A0. How about A2? How about A2? A2, does it change every time? No. Does it change just with A0? No. Sorry, here. No. But it changes if both A0 and A1 are 1. See? Every time it changes only 2 times because they become 1. So that's why at design you have A0 and A1 for the T flip-flop input for third bit. And the beauty of this design is if you have higher number of bits in your counter, here I'm talking about 3-bit counter. If you have 4-bit, 5-bit, 6-bit higher, you just add number of T flip-flops and make your logic like this. For 4-bit, same thing as A0, A1, A2, and A3 will change when all three A0, A1, A3 are 1, and so on. If you add number of bits, similar logic will apply to your design, which makes it simpler to implementation. That's why we use T flip-flops so in counter designer. Doesn't mean that's the only way. You can do that with D flip-flop, with JK flip-flop, but you definitely need more logic. Your circuit will become more expensive. Here is the implementation of the circuit, as I mentioned, and it's a 3-bit up counter. This is a 3-bit up counter. As another example, let's have a look at this circuit. Well, I'll give you a state diagram, not a description, telling you that there's a state diagram like this. Tell me that how many flip-flops required to design a circuit for this state diagram. How many flip-flops you need? 2 flip-flops. Why? Because you have 3 states, and to represent 3 states in binary, you need 2 bits, and 2 flip-flops will be enough, right? This state diagram represents which one? A Mealy or Moore machine. Is it a Mealy machine or Moore machine? Check it out. For a state diagram or for a circuit to be Moore, the only thing is you have to check all the states. All states. If by knowing the state, you can say what is the output, at each state, output always must be the same. Look at this. State S0, change the color. At S0, if I'm at S0, my output always will be 0. See, because I either coming from this way, which makes my output 0, or from this way, which makes my output 0. So S0 is good. Follows that. How about S1? For S1, if you're coming from this way, your output is 0. If you're coming from S1, your output is 0. And that's it. Yeah, S1 is also good. How about S2? S2, if you're coming from this way, your output is 0, but if you're coming this way, your output is 1. So if you're at S2, and that's the only thing you know, right? You can't tell what is the output right now, unless you know where you have been before. What was the previous state? Means output depends on input directly. So this is a Mealy machine. All right, so that's the other answer. Now, design the circuit using D flip-flop, T flip-flop, or JK flip-flop. Same strategy as we had before. We have to have transition table. We have to assign codes to our states. Then using D or T or JK flip-flop by looking at their state transition table, we do design, finding the appropriate number of K maps for each input. Before doing that, I want to answer this question, a claim which I made before. If I have a milling machine, can I make it a Moore machine? The answer was yes. The only thing you need to do is focusing on your weakness, on the state which doesn't follow the rule, state which might have two different outputs if you are in that state. So state S0 was good, state S1 was good, because if you're at S0 or S1, you definitely can say your output is 0. You don't need to know where did you come to this state, how did you land into this state, but S2 was the one which didn't follow this one. So the basic strategy is, if you have a state which give you different outputs, you might have different outputs at that state. What you do, you split that state in two, right? So I have S2, I make another state S2 prime or S3, right? Opposite of minimization. And with that, every transition, so these two are basically equivalent states, unless well, one of them will give me output 0 always, the other one will give me output 1 always. So it means those transitions which are coming from somewhere and giving me output 0 will go to just one of them. Those which give me output 1 go to the other one. Okay, how to do that? Well, same state diagram. I focus on these two. You see, these two transitions are giving me two different outputs. I'm going to split those into two states. As you can see, state S2 and state S prime 2. If I have that, how transition will happen, right? Those arrows which are coming out of S2 must come out of both S2 and S prime 2. So I have the arrow going to S0. I have arrow going from S2 and S2 prime. So these also will become doubled. Or if I have one transition from here to here, see, I have to do that from both, okay? With the difference here. This, since producing output 1, only lands up on S2 prime. You see, for this one goes here, but for itself goes to itself, right? And the other inputs, so inputs which produce different outputs will go only to one of them. See, this S0 will go only to this one, not to this one, not to S2 prime, not going here, just going here, right? In that case, these two, well, if you somehow you want to go back and merge these two states, these two are equal. These two states are equal, but giving you different outputs. Different output if, S1 doesn't go to S2 S2 prime directly. It goes to S2 and from S2 to S2 prime. And S2 prime or S2 to S2 doesn't go to S2 itself, it goes to S2 prime this time. And that gives me a Moore machine. So there will be a transform from milli to Moore machine like that. So this new state diagram is a milli state diagram. We are lucky this time. We are very lucky this time because, well, we had 3 states and we ended up to 4 states, and we still need only 2 flip-flops, not more than that. So which is a good thing, which is a good thing. In many cases, when you transform a milling machine to a Moore machine, you might end up to extra flip-flops. Well, definitely extra circuits, because here the original circuit was probably simpler, but this one is a bit more, right? A bit more circuit, but worth it in many cases. More machines give you a better, more stable design compared with milling machines. Sometimes you definitely want a Moore machine, never going for milling machine because of timing hazard and difficulty which might happen in transition between different values between clocks. Now, if I want to design the circuit, next step is assign coding the states. Well, the S0 one coding will be this, as we do. Another one can be this for the original circuit, not for the Moore for the Moore one, for the milli circuit, or can be this. I discussed that in class, and you know already. Or you can go for a higher number of flip-flops if you wish, with some redundancy. Remember, redundancy means having extra circuit than you need, but doesn't mean that you're wasting. There might be a reason. There might be a reason on that to make your circuit well, to have more stable behavior or better behavior in some cases. After that, we can build up the circuit. We can build up the transition table, K-map, and circuit after that. So question, which code is better? What are the costs and benefits of each coding, as we discussed? And can you design codes with only one bit difference between neighbor states? Right, which is also can be challenging, with minimum Hamming distance. To do so, we know that there is a transition between S1 and S0, S1, and S2. So all three are neighbors, right? And also S1 and S2 are neighbors. So you need, if you have that, with minimum Hamming distance between all three, you definitely need more than 2 bits. With 2 bits, you can't do that mathematically. We can prove that you need a minimum number of bits to have a minimum Hamming distance between your states. Again, in this class, you don't need to worry about details of that, but keep that in mind that it can be a very, very interesting challenge if you want to implement it. Okay, so state transition. Based on coding, as we had, well, we pick this coding, the basic one, as we use. We make the table like previous examples. You have transition from current state to next state and input. So how many K maps you need? You need one K map for A, one K map for B, and one output. If you use D flip-flop or T flip-flop. If you use JK flip-flop, you need two K maps for A, for J and K, and two K maps for B, J and K, and one K map for Y, right? What is the size of your K maps? There are 3 variable K maps because you have A, B as current state, and X as your input for the K maps. So let's do it with D flip-flop. If you have D flip-flops, answers will be these. Similar to what we did before. And circuit can be designed based on what you had as outcome of your K maps. for DA, DB, and Y. So circuit will be implemented. If you want to design that with T flip-flop, same strategy. You have to have your K-maps again for TA, TB, and output. And using this, you can design your T flip-flop based circuit as well, similar to what we did. I strongly suggest go step by step, try to understand, try to find my mistakes. I might have done that. Just double check to see every single entry of the K-maps are correct. And circuit implementation based on that will be same thing. So you do have output will be the same, similar to what we did for D flip-flop, and this one will give you the circuit design. For JK flip-flop, however, you need, again, I keep this in front of me all the time when I want to design. You need J and K for A state and J and K for B state, as we see here. This also gives me another set of design circuits to implement, and with JK flip-flop using those tables, you will have circuits. Super simple. You know, in this one, it's just for our neighbor. For this one, you have these two neighbors. For this one, you have these two as neighbors. For this one, you have these two and these four as neighbors to simplify your design. To reduce states, which is a step we want to implement in many circuit design. It makes a big difference how to reduce those. These days, mostly softwares can do that for us, algorithm, but there are basic calculations. You have to remember when we talk about cost of a circuit, it's not just number of components, number of gates. That's what we normally use as cost in this class, but in more advanced approach, in higher levels of design approach, you have to remember that cost can have deeper meaning. Cost might be speed of your, latency or speed you need for your circuit. It can be number of components. It can be defined as power consumption of your circuit. It can be defined as the silicon area your circuit needs. So be careful with the concept of cost, right? But in this class, we refer to the number of gates as cost. However, next year in more advanced courses, you see a deeper concept of the implementation cost. State reduction algorithms are concerned with the procedure of reducing the number of states in a state table or in a state diagram. Remember, since m flip-flops produce 2 to the power of m states, a reduction in the number of states may or may not result in a reduction in number of flip-flops because there is a gap. If you have 2 to the power of 3 gives you 8 different states, but up to 8 different states. So if you have 5 states to 8 states, all of them need 3 flip-flops. So if you reduce your 8 to 6 or 5, doesn't make any difference. You still need 3 flip-flops. And also can result in a smaller number of gates in your combinational circuit. As an example, look at this state diagram. You see we have A, B, C, D, E, F, G, right? Seven different states, and transition between the states has been transferred to this table. You see A goes to A or B to C and D for different transitions. To find equivalent states to be combined together, I have to look into transition between these states. Okay. First, we need the state table. It is more convenient to apply procedures for state reduction with the use of table rather than diagram. In diagram, it might look confusing to following state transitions. Two states are equivalent if, for each member of the set of input, they give exactly the same output and send the circuit either to the same state or to an equivalent state. See, two important characteristics. They have to give you same next states and same outputs in that transition. The procedure of removing a state and replacing it by its equivalent is demonstrated in the table. As you can see, two states have been combined together, and you have a smaller state diagram for your circuit.